Swayam Prabha. Digital India. Educated India.
Let me explain couple of approaches for recognizing the language or deciding the language palindrome, right? So palindrome is the class of strings that read the same way from left to right, right? So the word level, for instance, right? The word noon, it reads the same way back and forth, right? The word madam, for instance, right? So these are palindromes, right? However, some other word like friend is not a palindrome, right? Local is not a palindrome, right? So how would we check if a given string is a palindrome, right? So suppose the string was written in the input tape, right? So maybe I'll just write something. So let's say 10100101. Obviously this is a palindrome. So what you would do is, suppose there are n symbols, let's say the length of W is n, right? Then what would you do? You want to, so to check that this is a palindrome, what you can do is the following, right? You'll read the first symbol, right? And then go to the last symbol and see whether they are the same. Okay. If they are not the same, you can immediately reject, right? If they are the same, now you can look at the second last symbol and then come to the second symbol from the left point and check whether they are the same. If they are the same, then you continue. If they are not the same, you reject, right? So now you check the third symbol and the third last symbol, and then you keep doing this, right? So this, and basically you check first and this last, second last and the second, third last and the third, and so on. If at any point there is a mismatch, you reject. Otherwise you come to the end and then you accept, right? That's what we are doing here for maybe this. That's what we are doing here for each. So we check W1, which is the first symbol, Wn, which is the last, then W2, which is the second symbol, n-1, which is the second last, and so on. And you accept if for all I less than or equal to half the length of the string, if Wi is equal to Wn plus 1 minus I. So if the string is palindrome, these two should be the same. Otherwise you complete and then you reject, right? Otherwise you reject. If even for one I, Wi is not equal to Wn plus 1 minus I, you reject. And how much time does it take? So time, again, it's the number of steps, right? So now let us see what it takes. So it starts here from the leftmost point, and then it goes to the rightmost point. So this is n-1 steps. Then it comes back to the second point, which is n-2 steps. Then it goes to the third last, which is n-3 steps, and so on. So this takes, if you add up all of this takes order n square, or this is something that adds up to asymptotically n squared, right? So the Turing machine, to do all this checking, takes n squared number of steps. This means this procedure takes n squared time, right? So now this is going to be how we are going to approach things, right? Because we are going to closely measure how much time it takes, right? Now let's look at another algorithm, but we'll assume that we have two tapes, right? So maybe let's say W1, W2, W3, etc. Wn is this there in tape 1. So what we do is we copy this to tape 2. And then what we do is that we scan the tape from left to right on tape 1, and we bring the tape head to the rightmost in tape 2, and we scan the tape right to left on tape 2. So it's like this. So first we check, is W1 is W1 the same as Wn? Because the tape 1 head will be reading W1 and tape 2 head will be reading Wn. Are these two the same? If they are the same, we proceed. If they are not, we reject. Right? And then if they are the same, the head on tape 1 reads W2, while that on tape 2 reads Wn minus 1. And if that is also the same, then we go to the third symbol from the left on tape 1 and third symbol from the right on tape 2, W3 and Wn minus 2, and so on. And so essentially we are checking the same things, but this approach is faster. Why is that? So what did we do first? We first needed to copy the content of tape 1 to tape 2. So if there are n symbols, this takes n time. Okay, so this takes order n time. And then we move the head of the tape 2 to the rightmost end. That's also order n time. Now we need to scan the input, the tape 1 from left to right and tape 2 from right to left. That also takes order n time. So every step is n time. So the total time taken is On. So this algorithm, it takes order n time or big O of n time, whereas the previous one took big O of n square time, right? But we needed 2 tapes here, right? So this is more efficient, less time taken, but we needed 2 tapes, right? So we are actually, if you see, the 2 tapes correspond to using more space, right? So there is some kind of a time space trade-off. We are using more space but ending up using less time. So suppose we have more space available but we want to do it really quickly, this may be better, right? So again, so this says that, so anyway, so this also shows that palindrome is in, this also shows that palindrome is in P, right? Because n or n squared both are polynomial time, right? Right. So now let us let me just see what is, okay, now let us see a general result, right? So we saw that palindrome takes n time on a 2 tape machine but n squared time on a single tape machine. Now let us try to generalize this. So suppose there is a Turing machine or a multi-tape Turing machine, multi-tape deterministic Turing machine that runs in time Tn, okay, right? A multi-tape deterministic Turing machine that runs in time Tn. But now if you remember, when we studied multi-tape Turing machine and the equivalence to single tape Turing machine, we saw that anything that a multi-tape Turing machine can do can also be done by a single tape Turing machine, right? What this theorem states is that the single tape Turing machine, to do the same, decide the same thing, same language as the multi-tape Turing machine, takes time order Tn squared. So if the multi-tape Turing machine takes Tn time, the single tape Turing machine takes only Tn squared time. So it takes more time, but the more time is not unbounded, it's bounded by the square of this, right? And so for instance, if multi-tape Turing machine takes n time, which is what is happening here, the single tape Turing machine takes n squared, no more than n squared time, or there is a single tape Turing machine that takes no more than n squared time. So let's see why that is the case, right? So in fact, the proof is pretty much similar to what we saw when we saw that multi-tape Turing machines and single tape Turing machines are equivalent. This was theorem 3.13, which we covered in lecture 29 of our course, right? So all that we are doing is, it's exactly the same proof, but there our goal was to just say that anything a multi-tape Turing machine can do, single tape machine can also do. But now that we are bothered about how many steps it takes or the time it takes, we'll have to analyze the steps it takes, right? So let k be the number of tapes that the multi-tape Turing machine has. Now we want to simulate it in a single tape Turing machine. So you may recall this, but nevertheless I will just briefly explain. Basically the k tape contents, we include it in a single tape, okay? So and we use these delimiters right, which we denote by the hash symbol, right? And so basically we are virtually dividing the single tape into k tapes, right? And then we also have this marker for the heads. So we'll have some symbols will be special will have this. So every virtual tape will contain one place where this marker is there, which indicates where the head is in the multi-tape machine, right? So I'm not getting into the details, because if you forgot what the full proof was, you can refer back to lecture 29, right? So where we explain this in detail. So what the single tape simulation tries to do is to now go scan the tape from left to right, right? And when it scans the tape from left to right, it remembers where the head positions are, right? So it knows where the k, or it will try to see where the k head positions are, okay? And then once it knows the k head positions, it knows what is the next step that the multi-tape Turing machine has to take. So now it has to reflect that change in the single tape, which is kind of virtually encoding the multiple tapes. So now to make the change, it makes another pass from left to right. So if it needs to move the head position one place, if it needs to overwrite, all that it will do in that second pass. So basically two passes, one to scan, and then it figures out what is the next step, and then another pass to implement the change, right? And that's the rough algorithm. So initially, just one more point. So initially we have the input in tape 1, followed by the other tapes being blank, right? Which is how it should be, and all the tape heads are at the leftmost, and then the tape heads will move, and the tapes will, like, content will be written on the tapes as we go along, right? So how much time does this take, right? So the algorithm is exactly the same as what I had said when we saw chapter 3, right? But now the question is, how much time does it take, right? So let's see. So for that, what is the biggest time consuming factor here? So for each step of the multi-tape Turing machine, the single tape Turing machine has to do one pass to read and understand what the head positions are, and then another pass to implement the changes. So two passes, right? But two passes, how long? Right? There are k tapes. However long these k tapes are, or how long can the k tapes have any content, right? So if you think about it, these are tapes corresponding to the multi-tape machine. So if the multi-tape machine runs in t time, the worst that the tape can, how much can the tape get filled up? The tape can get filled up. So if there is a Turing machine and this is a multi-tape machine, let's say. So this tape, let's say every step it moves one step to the right. Every step it moves one step to the right, and then in t steps it can fill up to t spots, right? So which means but it cannot do any more than that. In t steps it can only move t steps. So which means each of these virtual tapes can take up to tn, can be up to tn long in the worst case. It may not even be that much, because if it moves left, then it's not going to fill up t. But the worst case is t. Each of these tapes can be t cells long. But then we have all these hash symbols and they have k tapes. So roughly, let us say it takes k times tn. This takes k times tn space because of the k tapes, right? So I am just ignoring the hash because it's not really going to contribute a significant amount. So the tape, this is k times tn long, right? So maybe I'll just write that. And to make two passes, it takes 2 times k times tn, right? So that to make two passes, and all of this is to make just one pass of the single, or one step of the multi-tape Turing machine. So when the multi-tape machine takes one step, the single tape Turing machine has to make 2 times k times tn steps, right? But then how many steps does the multi-tape Turing machine take? So by the assumption, the multi-tape Turing machine runs in time Tn, right? By assumption, this is the time it takes. To simulate Tn steps of the computation of the multi-tape Turing machine, we need to multiply Tn with the time it takes to accomplish or execute each step, which is 2 times k times Tn. So Tn number of steps of the multi-tape Turing machine and the time it takes to execute each step, which is 2 times k times Tn. So altogether multiplying, we get 2 times k times Tn squared. Right? So 2 and k are constants. 2 is a constant, k is the number of tapes, which is also a constant. So the total running time is O Tn squared, right, which is what we claimed here. Right. So all that says that if the running time of the single multi-tape Turing machine is Tn, then the single tape simulation takes at most Tn squared time asymptotically, right, which kind of matched what happened in the case of palindrome. In a way, it is good to know. Like, it's not like if the multi-tape Turing machine has k tapes, it is not Tn power k, for instance, right? So no matter how many tapes it takes, this is still squared. This is not bigger exponent, right? Of course, k features here as a constant in the O notation, but that is absorbed by the O notation. But it does. If it featured here, it would have been worse. But this dependence is something that is slightly less, right? Anyway, just to remind again, class P is a class of problems whose running time is n power k for some constant k in a deterministic Turing machine, and always polynomial running time is considered to be more efficient than an exponential running time. Meaning, whenever we have a choice between n power k and k power n power k is much faster growing, much slower growing, so much less time than exponential. Okay. So now I want to just go through some problems. I won't explain them to great detail, but some problems and say how much time it takes for each of them, right? So one problem is given a graph, is it connected, right? So the answer is this is polynomial time, this is in P. You can do BFS or DFS, right? So do DFS or BFS. So this is in P, right? Because given the graph, breadth first search or depth first search traversal algorithm is something known, and that tells you whether the graph is connected or not. The other problem is whether the graph is three colorable. Three colorable means can a graph, right, be colored using three colors such that no two neighboring vertices get the same color, right? So this small graph that I have drawn cannot be colored using three colors, whereas this graph that I am drawing, it can be colored using three colors. So given a graph, can this be colored using three colors? And this is as of now not known to be in P. Of course, you can try all possible three colorings, but that takes exponential time, right? If the graph has n vertices, to try out all possible colorings using three colors, it takes 3 power n time. That is 3 power n, which is not polynomial, right? There is no known polynomial time algorithm for this problem. Relatively prime. Given two integers x and y, are they relatively prime? So meaning, is the highest common factor or the highest common divisor, or sometimes known as GCD, right? So in other words, is it like we are asking, is GCD of x, y equal to 1, right? This will happen only when they are relatively prime. Is there any common factor? In fact, this is known to be in P. There is something called Euclidean algorithm that you can, that tells you how to do this. You basically divide the bigger number with the smaller. So if x is bigger and y is smaller, you divide x by y, and then if y is a divisor of x, then y is the they are not relatively prime, because assuming y is greater than 1, if y does not cleanly divide x, then you take the remainder and then repeat. Okay, so I don't want to get into details, but there is a clean algorithm for this. So next question is, given a number given a number n, right, is n prime, right? This is also a polynomial time problem. There is a polynomial time algorithm for it. However, this was some problem that kind of confounded computer scientists for a long time, right? This was only discovered in 2002, maybe around 20 years back. So one may wonder, what is the big deal here? Like given a number, you want to test whether it is prime. Can you just not try out all possible, like, let's say you are given some number, let's say 241. You try out factors that 241 is not a multiple of 2. Is it a multiple of 3? Then you see it's not a multiple of 3. Then it's a multiple of, not a multiple of 5. You try out all possible prime factors, right? And then you have to rule out everything till square root of n or something, right? However, this turns out to be, the running time for this turns out to be something like roughly, and it is enough to do up to the factors up to square root n, because it has to have some non-trivial factor which is at most square root n, because two factors above square root n will give some number bigger than n, right? But this is not, this particular approach that I suggested is not polynomial time. Okay, maybe I'll just write here, for prime trying out all prime factors up to square root n is not a polynomial time approach. This is because so the problem here is that one may think that square root n is polynomial in capital N, which is correct. The thing is that the running time should be polynomial in the length of the input. Okay, so square root n is not polynomial in the length of the input, which is like log n. So if you have a number, let's say 100, it takes 7 bits to write down that number. So you don't write the number, the length of the length of the input is not 100. The input is 100, but the length is just log of 100. So in terms of the length of the input, square root n is actually exponential time, right? So let's say log n is equal to, suppose this is equal to x, right? Or maybe I'll just call it small n, small n. Then square root n is like, it's like 2 power n, square root of 2 power n, which is like 2 power n by 2 or something, which is, anyway, it's exponential in, so this is exponential in n. Which is the so when I say polynomial time, every time it is in terms of the length of the input. So the straightforward algorithm that we are talking about, that is just trying out all possible prime factors up to square root of that number, it is a correct algorithm, but this is not a polynomial time algorithm. This is because this takes time that is exponential in the input length, right? But there is another approach which actually is polynomial time, which I'll not say, I'll not explain, but it is also non-trivial. After a long time, there are many years people were looking at it. The problem prime is in polynomial time, but this approach does not work, right? The next one is computation. Given A and B, two n by n matrices, you want to multiply them. This is in polynomial time. There is a standard n cubed algorithm, but there are slightly better algorithms also, right? So finally, we have two more problems. One is TSP, traveling salesman problem. So traveling salesman problem, maybe I'll just briefly describe. It's like this: given a map, right? And let's say you are a salesman and you are starting from some node, let's say this one, this is like home. Your goal is to visit all these cities. So these dots are cities, right? So these are cities. These dots are cities. So this is a traveling salesman problem, sometimes called TSP. Your goal is to visit all these cities and then come back to the home, right? So you have to have some tour, right? Something like this. So this is a tour. Now I want to do this in the most efficient manner, in the shortest possible distance. So that is a traveling salesman problem. Given all the cities and the layout and the distances, what is the shortest possible way? In fact, this is not known to be in P. So it seems like a simple problem, but this is not known to be in P. And finally, one more language that I will just briefly describe. Maybe I'll just push this down a bit. This is called subset sum. So given a subset, right? So something like, let's say, given a set, let's say 1, 3, 2, or maybe not 2, 7, 10, 16, right? Now I am asking, is there a subset that sums to 12, right? Is there a subset of this that sums to 12? I think the answer is no, but the question is a subset that sums to 12. So maybe I'll just say T equal to 12. So given a set S and a target T, is there a subset of S that sums to T? That is the question. And surprisingly, this also is not known to be in P. Right. So this is just to give some of these. I'll explain why of course, for those that are in P, the algorithm is known. For those that are not in P, it's just that we don't know. And for some of these problems, let's say traveling salesman problem, subset sum, etc., there is some evidence as to why it may be unlikely that we may never get to know whether, or it's going to be very hard to get to know whether it is in P or not, right? And so even so for 3-colorability, right? Again, these are some example problems, and I'm just explaining what is known about them. Now let me just quickly recap. So we started the complexity theory. We said that we are going to be considering only decidable languages and studying them based on how much resources they use, right? So this chapter is about time complexity. So where time means the number of steps taken by a Turing machine to decide on a certain input, right? So we first defined running time complexity, the O notation. We defined d time Tn, which is a class of all computational problems that can be decided in OTN time. We defined P to be the set of all computational problems that can be decided in polynomial time. And we explained this result that if a multi-tape Turing machine runs in time Tn, there is an equivalent single-tape Turing machine that runs in Tn squared, followed by a bunch of problems, and we saw how much how we can solve them, and in some cases we explained what is known about this, whether this is known to be in P, not known to be in P, and so on, right? And that pretty much sums up what I wanted to say in this lecture number 45. So in the next lecture we'll see more about complexity theory. We'll see more. We'll see other types of other aspects of time complexity. So thank you.